All right. We're going to now take a little, it may seem like a detour from matrices and some of the matrix theory we've been doing, and we're going to build up some of the background information we need of what space we're working in, right? These matrices or these vectors, these all have a geometric interpretation inside some dimensional space, right? For example, when you're looking at adding two vectors, well, those two vectors, there's a geometric interpretation of what the addition of two vectors means, just for an example. And so what we'll do here in today, and then even into Tuesday some a little bit, is we'll start to look at what space we're working in, right? And so we'll start just by here, this Rn, this R here is called a Blackboard R. This stands for n-dimensional Euclidean space. So just to build some intuition here, because unfortunately for n bigger than 3, our mind loses an idea of what that means or would even look like. So let's just start with n equals 1. When n equals 1, we have just the real numbers, right? So we would have R, and this is the real numbers. And a geometric interpretation of the real numbers, right? We've seen it since grade school, probably. We have our number line, we mark 0, and then we know that this tends off towards positive infinity to the right, and then negative infinity tends towards negative infinity to the left, right? And we can talk about points on the number line being in a one-to-one correspondence with the real numbers, right? So if we have X here, you know, I mean, in our kind of more recent notation, we would say like X is an element of the real numbers here. And basically what this means is we just have some number, right? Well, we also have, for some point, we can think about vectors in the real numbers, right? Say here, like some vector V, they don't necessarily have to start at 0 or 10 to the right even. So we have these notions of vectors in the real numbers. What about like when n is 2, right? We're very comfortable with the n equals 1 case. Well, what about n equals 2? When n equals 2, we have the xy plane, right? You could think about this as the xy plane. Another way you may see R2 written, or two-dimensional Euclidean space, is R cross R here. This is a Cartesian product. And basically what it is you take a copy of the first space, right? So the first space here is R. And at every point in R, you have a copy of the other space, kind of perpendicular to it. So if you think, we have all these copies of the real numbers perpendicular to the first copy of the real numbers. And this is, right, there's an infinite number of these because there's an infinite number of points on R. Well, in this whole space, it's usually never drawn like that, but this whole space is the xy plane. So we have, you know, sometimes we'll see, or maybe let's do like x1, x2 here, right? Where you have points x1, x2. If you would like a formal definition of the xy plane in set notation, these are the points x1, x2, such that, remember the bar in set notation means such that, so x1, x2, such that x1 is an element of R and x2 is an element of R, right? And so what we have here is you pick a number on one real line, you pick another number on the other, you have x1, x2. This uniquely determines a point in the plane, right? And so these are points, we also have vectors in two-dimensional space as well, right? So for example, we could have the vector v here, maybe starting from the origin, going to the point x1, x2, or, in general, you can have a vector starting and ending anywhere. Maybe call this w. Let's do one more just to kind of fully exhaust our dimensions here that we can picture at least. When n is 3, well, we have R3, which is R2 cross R, which is R cross R cross R. And so if you can imagine here, maybe playing into this Cartesian product to try to understand what this is doing, well, we have R2, which is a copy. We have the XY plane here, right? So you can imagine here's our R2. And then at every point of R2, we have a copy of the real numbers perpendicular to R2. And so at every point on this plane, maybe let's go back. That's kind of a bad, maybe this would look better. Right. And of course, there's an infinite number of points on a plane. And so there's an infinite number of these places where you're getting these lines, this copy of R, right? And if you looked at all of this, you took the union of all of this, what you would get is just the XYZ coordinate system in three-dimensional space that we're used to. And again, let's stick with our X1, X2, X3 here, right? And so points in R3 are determined by X1, X2, X3. If you would like an explicit description of R3, let me give myself some room. X1, R3 would be the set of points X1, X2, X3, such that Xi is an element of R for all I between 1 and 3, right? So this is just a description of, oh, sorry, here, I forgot to close my point. A description of the collection of points in three-dimensional space, which makes up our Euclidean space here. Again, we could have vectors in R3. We'll talk more about vectors later, but we can have points and vectors and things like this. Vectors being quantities with both a direction and a magnitude, right? We'll talk about those more explicitly after we give a kind of a generalized definition of Rn. Okay. So what about R4, right? Well, for R4, we would have to try to picture. So here's, right, this would be R3 cross R. And we would need to think about, well, we have three-dimensional space, and then we need something perpendicular to all three of these, right? So somehow we would need, like at each point of R3, we would need something perpendicular to all of this, but we run out of spatial room, or really in our head, at least, we run out of room in our head because we can only picture 3 perpendicular dimensions. There is a notion, while I'm on the topic, there is a notion of R3 plus 1. And of course, 3 plus 1 is equal to 4, but these are interpreted slightly differently sometimes. And I doubt we get into the difference in this course, but it's kind of interesting to talk about. So R4 here, this would represent 4 spatial dimensions. And here, R3 plus 1 would represent 3 spatial dimensions. Plus 1 time dimension. And so our minds are better at picturing what's going on over here because we exhibit, or like we live and experience time linearly, right? If you kind of think about, say, my phone here as being a 4-dimensional object, as, well, it's in 3 dimensions, but as time goes forward, this phone moves, right? There's my wife and I. This phone moves, and the 4-dimensional object would be kind of like the trace, if you will, like from start to finish of the whole thing. And so you can kind of think about 4-dimensional objects that way when you think about the 3 spatial dimensions plus 1 time dimension aspect. Certainly trying to just picture 4 spatial dimensions is pretty hard. If anybody can do it, let me know. Maybe you can teach me. But you know, we won't really need to picture these things necessarily. We can still do the algebra and everything without being able to picture it. That's one benefit of our minds, is even though we can't picture it, we can still do computations and things like this, because it's just keeping track of more dimensions and more numbers. So, well, instead of just giving the definition of R4 and then et cetera, why don't we just give a definition of Rn in general? So here, let's write a definition. Here's n-dimensional Euclidean space. So we have Rn is going to be the set of points x1, x2, et cetera, through xn, such that xi is an element of the reals for all I, where I lives between 1 and n, right? And so this is just an index. I is an index here running from 1 to n. And basically what we're saying is we have these ordered tuples, or these ordered collections of points where each point is a real number, right? It's just the generalization of saying x1, x2, x3, like x1's in R, x2 is in R, x3 is in R, right? So this is just a generalization to an arbitrary dimensional space. So what would vectors look like in space, right? So sometimes I'll just refer to this as in space, right? Or if we're in 2 space, 3 space, more often than not, I'll say Rn, R2, R3, and we'll get the idea there. But what would vectors look like in space? So let's look at vectors in R. And really, basically what we're doing here is generalizing a lot of the notions of Calc 3, right? In Calc 3, we did all this vector algebra and vector calculus with in dimensions 2 and 3. We won't get so much into the vector calculus aspect here, but we'll do plenty of like vector algebra from Calc 3 that's now generalized to an arbitrary dimensional space, and not just being confined to kind of dimension 2 and dimension 3. Of course, that's necessary to learn first because that's what we can understand and picture the best. But now we're going to generalize here and see if we can understand these notions of vector algebra, but in arbitrary dimensions. So let's say we're in n-dimensional space. Well, we're going to write vectors v. You know, in Calc 3, we saw them listed as like, maybe I'll use v for vector components, right? v1, v2, v3, etc. v sub n. Like an example, if you had, let's say n equals 2, well, we're in the xy plane here, and we have, let's look at the vector v that's given by 2, 3, right? We know the first entry said, okay, this is the x component, and the second component was the y component, right? And so this notation here told us we would go 2 units in the x direction, 3 units in the y direction, and then we have a vector here, right? And we know 2 vectors are equivalent if their components are the same. So the vector 2, 3, maybe we're at 4, and then we go out to 6, and then up to, so 2, 3, we'd go 6, and then up 3. So we'd go from 4, 3 to 6, 6, right? This is the same vector. And so like basically parallel copies of a vector with the same magnitude and same direction are equivalent, right? There's no specification of base point here. we will start to view these, we'll kind of change our notation to be consistent with the matrix theory that we're doing here. So let's change our notation. So let's pass from V1, V2, Vn to V will be written as a column vector, V1 through Vn. We'll also see this written as the transpose of a row vector. So I'll kind of use these synonymously and probably sometimes without even mentioning, right? We're just going to refer to vectors as column vectors. And if they're written as a row vector, we'll usually slap on this transpose operation so that we know we're still looking at a row vector. So what is a position vector, right? I was talking about these kind of like parallel transports of a vector and it's all being the same, but we can still talk about a specific kind of, or specific kinds of vectors. So let's look at a position vector here. So if we're at the position, or let's say point, let's say if we're at the point P, which is given by P1 all the way up to P sub n, right? So those are your coordinates of the point in n-dimensional space here. And of course, the biggest dimension I can draw is 3, but humor me, use your imagination here. So P, this is the point P1, P2, Pn here. And then a position vector is the vector V that has components that are the same as the point. So on the first component of the vector, it's the same as the first component of the point. So P1 through Pn here, right? This vector would be V. And another way you'll see this written to specify where exactly this is at is we'll write this V as the point 0, P. And basically what this is the vector starting at 0, 0, 0, and ending at P, right? So in general, though, our starting point doesn't have to be 0. What if we had the vector PQ, right? This is starting, so this is representing the vector starting at P and ending at Q. So let's say we have 2 points P given by P1 through Pn, and then Q given by Q1 through Qn here. Well, then what is the point PQ? Or excuse me, not the point. The point is it's a vector, right? No pun intended. So if we have the point P and the point Q, the vector starting at P and ending at Q is defined to be, well, if you'd like, that's 0, Q minus 0, P. This is a little bit ill-defined because we haven't talked about vector addition in this context yet, but we've seen addition of matrices, so we have addition of vectors, right? We'll go into that more in a little bit, but kind of how this is defined, well, if you would like this, and I'll write this as a row vector transpose for the sake of room, this would be Q1 minus P1 for the first entry, Q2 minus P2 for the second, all the way to Qn minus Pn for the third. So this is how you would define a vector between 2 points. Let's do a little example, something that we saw all the time in Calc 3 if you've taken it. So let's do an R3 example. So let's let P be the point 2, -8, 5. And let's let Q be the point 0, 9, 4. And you may ask, what is PQ? Right? Well, PQ is going to be, well, we take Q, we basically take the Q components minus the P components. So we're going to have 0 minus 2. for the first one, and we'll have 9 minus -8, and then we'll have 4 minus 5. And here we're going to get -2, 17, -1. This would be the vector between these 2 points, right? And if you were to like map this out in 3D space, we have 2, so let's say X, Y, Z. We have 2, let's say -8's out here. And then 5 is up here. So this would be our point P. Our point Q would be 0, 9, 4, right? And then what we're looking at is this vector here. And basically what we're saying is we're going down 2 units in the X direction, which makes sense. The X direction, as I've drawn it, the positive X direction would be coming out of the screen. And so the negative X direction would be going into the screen. So you can imagine to get from P to Q, we're going into the screen 2 units, 17 units to the right, and then 1 unit down, right? This would be kind of your interpretation of this vector in 3D space. Okay, so let's talk about some more types of vectors here. We have, well, what's our notion of equivalent vectors? For equivalent vectors, we say U, let's say we have 2 vectors, U1, U2, good band, all the way through UN transpose, and then we have V is V1, V2, Vn transpose, right? So these are still just column vectors in space. We say U and V are equivalent if U sub I equals V sub I for all I, right? Basically for every I in our index here. Remember, our index is just 1 through n because we have that many components of our vectors. And we just write this as U equals V, right? Pretty standard, but it's worth being explicit. So we have this notion of equivalent vectors. So if 2 vectors have different direction, they are not the same. If they have different magnitude, they're not the same, right? So they have to be identical in every component, which corresponds to them having exactly the same magnitude and direction. A very important type of vector or vectors, and this is specifically for R3, we have what are called the standard unit normal vectors. Usually I'll just refer these as like standard normal vectors or standard unit vector. I'll abbreviate so it's not standard unit normal vectors every single time. But what these are in 3-dimensional space, they're denoted by I hat, J hat, and K hat. And these are the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so we have these. What do these look like in 3-dimensional space? We have, let's draw I hat in red here. So this is the vector 1, 0, 0, right? Maybe I'll just write I hat here. So let's give ourselves units. That's 1 length, 1 length. So this would be I hat because it has direction 1 unit in the X direction and then no direction in the Y or Z directions. J hat is the same, but for the Y component, right? There's no direction of this vector in the Y or in the X or Z components, but it does fluctuate in Y. Let's look also at K hat, which is basically just 1 unit purely in the Z direction. So this is K hat. And if you'll notice, these vectors make a basis. We'll learn what that means later, but what we'll see is that any vector in R3 is a linear combination of these three vectors. So if we have U is the vector U1, U2, U3, right? Well, then U can always be written as a linear combination of U1 I hat plus U2 J hat plus U3 K hat, right? And so this means when any vector can be expressed as a linear combination of other vectors, we call these vectors a basis or a spanning set. This is not necessary vocabulary for the moment, but just so we hear it now, maybe it won't be so foreign when we come to that in the future. Okay, so I think I'm going to stop here for this video. And what I'd like to do for the next video is start to talk about some algebra in n-dimensional Euclidean space, right? So here I'm talking about like the sum of vectors, right? There's algebra going on here. And I have like scalar multiplication, right? You can see I'm multiplying the real number U1 times a vector. There's this algebra going on here, and we're fine with it in two-dimensional, three-dimensional space. But let's generalize this algebra to n-dimensional Euclidean space. So we'll talk about that in the next video.